All right, hello, welcome back to the Math Fun Room. In this video, I want to talk about hyperbolic functions. So again, as a summary of what we've done up to this point, we're kind of covering a chapter about derivatives here. And we've talked about the power rule, we've talked about differentiating exponentials, differentiating logarithms, differentiating sine, cosine functions, using the power rule and quotient rule. So as we talk about like all the different types of functions we can differentiate, another type of function we want to consider is what we call the hyperbolic function. Now, I prefer to write all of the notes of the topics that we discuss, but I wanted to give some background, some context to what a hyperbolic function is, and I didn't want to take the 20 minutes to write everything down. So I would recommend to you, as you watch these videos and take notes, pause the video after I mention something and write notes down for yourself. And then momentarily, we will go ahead and start writing like normal. So first of all, there are some connections or some similarities, I would say, between the standard trig functions and the hyperbolic trig functions. First of all, the hyperbolic trig functions can be thought of using Euler's formula. So Euler's formula is this formula we see here, e to the I theta. So if I have an exponential function, base c exponential, that has a domain that's complex, imaginary, we can break that up into a real and imaginary part. And if we think back to maybe an algebra class, we could write a complex number as a plus bi or a minus bi. So when we have an exponential that has a complex domain, complex input, we can write it as cosine theta plus I sine theta, right? Or e to the negative I theta would be cosine theta minus sine theta. So what we see here is the real part of the number is cosine theta, just like here the real part was the number a, and here the real part, the imaginary part is sine theta, because that's what multiplies the I, and here b would be the imaginary part. If we do some algebraic manipulation of this expression, we can see that cosine theta is e to the I theta plus e to the negative I theta over 2, and then sine theta really describes like the imaginary part of this number. If we solve for sine, right, that's the imaginary part of that complex number. So one way to think of defining, or the relationship through Euler's formula of hyperbolic sine and hyperbolic cosine, is we can think of the fact, we can think about this as we've ripped away the imaginary parts, if you will. So the hyperbolic cosine is defined as being e to the a plus e to the negative a over 2, right, where the input is a. And then hyperbolic sine can be thought of as e to the a minus e to the negative a over 2. Notice the similarities in these definitions. Hyperbolic sine has negative, hyperbolic cosine has positive. So this is one way to think about the definition of hyperbolic cosine and hyperbolic sine. And again, these would be those definitions that we would use. So in a calculus course, these are the definitions we write down, defining hyperbolic sine and hyperbolic cosine. Now, to make some connections or to compare the trig function sine and cosine to the hyperbolic trig functions, hyperbolic sine, hyperbolic cosine, if we think back to a trig class, a couple different ways we visualized hyperbolic cosine and hyperbolic sine. So if we looked at the unit circle, right, circle of radius 1, the x-coordinate of any point on the circle is defined as the cosine of the angle from the x-axis and the terminal side of the angle. So wherever this terminal side lied, we looked at the number t in this expression as an angle measure. So it looks like this angle measures, 45 degrees. If we go all the way to the y-axis, that's 90 degrees. Right? So this point lies at cosine of the angle, sine of the angle in the quadrant. Now when we define the trig functions, we think of basically like rise over run. We think of sides of our right triangle. So, down here, if we look at the definitions of these trig functions that we have, right, we defined this angle, right, we called this the angle t in the other problem, right? We always write that as usually theta. We can see this definition is using the letter A to label or discuss the angle measure, right, in this triangle here. or theta we have in this picture. So sine of theta was defined as being opposite over hypotenuse, and we can see that definition here, opposite over hypotenuse. Cosine of theta was defined as being adjacent over hypotenuse, and those were those definitions. Right, so based on these definitions, right, excuse me, we look at the relationship to the unit circle and the point on that unit circle. Now, if we look at the hyperbolic cosine and hyperbolic sine, and if I scroll back up here, based on Euler's formula, right, here was our definition. So we can see hyperbolic cosine of the input is e to the input plus e to the negative input over 2. And we can see here's that hyperbolic cosine definition right here. And then the hyperbolic sine definition was e to the x minus e to the negative x over 2. Now, first of all, a couple things to notice. This input x right here is not an angle measure, just like it was over here. So this was sine of an angle. This is not an angle. We don't interpret that as an angle. Excuse me. And same thing for all of these inputs. Hyperbolic cosine of x is e to the x plus e to the negative x over 2. And again, this comes from Euler's formula. So visually, we can talk about, and this is why they're named hyperbolic functions. This is the parabola x squared minus y squared equals 1. We could call this the unit parabola if we want. So x squared minus y squared equals 1 has this graph that we see in blue. And so the point on this hyperbola is defined as the x-coordinate being cosine t, the y-coordinate being hyperbolic sine of t. I get a little lazy and call this cosh of t and this sinh of t. So in these side-by-side comparisons, right, we're just looking at how are the trig functions defined and their kind of visual interpretation of a unit circle. Here's how the hyperbolic sine functions are defined, and here's their representation of a point on a hyperbola. All right, now when we're looking at this hyperbolic shape of a curve, there's some particular applications of interest that we could talk about, at least this level of a course. Now, the idea in these three pictures at the top are what we would call a catenary. So a catenary that I was underlining here, and catenary is the idea of like a weighted cable. So if we look at, like, let's say 2 towers and we have a weighted cable, it's going to have some sag to it. And this kind of looks like a parabolic function, a parabola, but it's not really. This is the exact form is a hyperbolic cosine. So if we place the origin between the two poles, right, the hyperbolic cosine describes the shape of that graph. And then ditto here, right, I have 2 poles, I have a weighted chain. This sag is described as a hyperbolic cosine function. And then here's a picture of a bridge, and the weighted bridge follows the shape of a hyperbola, right, the hyperbolic cosine function. And then we could also talk about planetary orbits, right? If we have planetary flight and we launch from Earth and we're going to get a gravity assist, we're going to slingshot around the moon to launch ourselves to Mars, then that also path of that slingshot is a hyperbolic function as well. So in a course like calculus, these may be some of the applications that you would look at for hyperbolic sine and hyperbolic cosine. There are other applications that you would see in a differential equations course. Of course, that's beyond the scope of this class, but not only are these some applications, but there are others. All right, now keep in mind, one of the main things we're doing in a calculus course is we're going to talk about the derivatives of these functions. We'll talk about their graphs. We'll talk about, remind ourselves that a derivative is a rate of change. And we're going to use those concepts. We're going to use the derivative formulas. We're going to measure slopes of curves, talk about velocities, which is a derivative as well. All right, so if we come back to these definitions of the hyperbolic functions and we think of, what are the graphs of the main three? What are the graphs of hyperbolic sine, hyperbolic cosine, and hyperbolic tangent? And one way to think of developing the graph, right, if I look at hyperbolic sine, this is really, if I split the fractions apart, this is really 1/2 e to the x. This is really negative 1/2 e to the negative x. So I'm adding together e to the x over 2 minus e to the negative x over 2. So if we graph 1/2 e to the x and we graph negative 1/2 e to the negative x, we can see that these are like asymptotes of my hyperbolic sine. And I add these values together for any x, I'm producing the output of hyperbolic sine. So hyperbolic sine looks kind of like a cubic function, right? But the exponentials are asymptotic to our hyperbolic sine function. If we look at the hyperbolic cosine, again, keep in mind if I split these fraction up, there's a plus sign here. So I have 1/2 e to the x plus positive e to the negative x over 2. So when we look graphically, here's 1/2 e to the x, here's 1/2 e to the negative x, and when I add those together, I get this shape that looks, kind of like a parabola, like we saw in those sagging, those weighted cables that had sag to them. And then all the other hyperbolic trig functions are defined in a very similar manner to the original the original trig functions. So hyperbolic tangent is defined as hyperbolic sine over hyperbolic cosine, and so on and so forth. These are reciprocals of the original three. Now, if I look at hyperbolic tangent, this graph looks almost like inverse tangent. If you remember, inverse tangent looks kind of like this. The asymptotes were pi over 2 and negative pi over 2, but for hyperbolic tangent, it is 1 and negative 1. So in scenarios where we graph, these are really the three main functions that we're going to look at. All right, so since we're talking about graphing, real quick, if we were going to graph these functions, some form of these functions with some graphing technology, I'm looking at a TI 84 calculator here. So I would hit the y equals key, and then, the trig functions actually have their own button on the face of the calculator. The hyperbolics do not. So we actually have to go to the catalog. If we look above the number 0 in blue, it says catalog. So let's say I want to graph hyperbolic sine. I'm going to hit secant 0. And then I want to point out to you up in the right hand corner is the letter A, and that's telling me that my caps lock is on. So instead of having to hit my down button and scroll all the way to the letter S to graph hyperbolic sine, I can just hit the letter S on my keyboard. So we notice in green above the LN key is the letter S. So I'm just going to punch the LN key because I'm in alpha lock, and it's going to jump me to the S's. And then I can just scroll down until I find hyperbolic sine. And what you'll notice is once we find hyperbolic sine, we also have hyperbolic cosine, inverse. Apologize. So I have hyperbolic sine, and then I have the inverse of hyperbolic sine. So I'm just talking about graphing hyperbolic sine. I highlight that, click enter, and then I plug in my domain of x. And then so when I graph, there's our graph of hyperbolic sine. So we could do a similar thing for hyperbolic cosine or hyperbolic tangent, go into the catalog to find those functions. Now if I'm using Desmos, I'm just going to type out the letters. So I just say y equals and do TANH. And then of x. So there's hyperbolic tangent. Right, now I'm on a keyboard on my desktop. Right, of course I could bring up the alpha expressions here. Here's my numeric menu. Here's my alpha menu here. And then, probably an easier way to do this is instead of going to the letter menu, letter keyboard, I can hit functions, and we can see that the hyperbolic functions are also defined in here as well. Okay, and then lastly, right, just like regular trig functions have identities, so do hyperbolic trig functions. And here's some of the most frequently used. We have 6 of them here. We have hyperbolic sine of negative x equals negative hyperbolic sine of x. And this is just because hyperbolic sine is an odd function. So f at negative x equals the negative of f at x. And then hyperbolic cosine is even, so there's a second identity. Remember that with regular trig functions, we have cosine squared plus sine squared equals 1. With hyperbolics, we have hyperbolic cosine squared minus hyperbolic sine squared equals 1. So we have a subtraction sign here. So cos squared minus sinh squared equals 1. Now, any of these identities is actually pretty simple to prove or derive. So if I was going to prove or derive this first formula, what I would do is plug in the definition of each of these functions. So I'd come back up here and I'd plug in the definition of hyperbolic cosine. I'd plug in the definition of hyperbolic sine. And then, I'd square those definitions and simplify, and I would end up getting 1 equals 1. So there's some textbooks where you would have a couple homework problems where you would, prove that one of these identities is true. Okay, so again, illustrating this guy here, go to my pen, right? And illustrating this guy here, I would plug in the definition of hyperbolic cosine. So I'd have 1/2 e to the x plus 1/2 e to the negative x, and then that's hyperbolic cosine's definition squared, and then I had hyperbolic sine's definition, so 1/2 e to the x minus 1/2 e to the negative x was its definition. I would square that, and I'm looking to show that I get 1 equals 1 here. So if I square the first expression, this is a binomial. When I square the first expression, I square the first number, 1/2 e to the x squared, and then I multiply these two and double, right? So multiply the 2 and double, and then I square the last. All right, so remember, this shortcut is that a plus b squared is a squared plus 2ab plus b squared. I'm just using that shortcut of squaring a binomial. Now, I want to square this as well, and let me see if I can squeeze this in. So first of all, let me simplify this, and we can see what this is actually going to become. So this is really 1/4, right? And when I have e to the x squared, remember when I have an exponent raised to an exponent, I multiply those exponents. So I really have e to the 2 times x. And then here is a half times a half, which is a quarter, times 2 is a half. So I'm going to have plus 1/2. And then when I multiply like bases, I add exponents. So I'd have e to the power of x plus negative x, which is e to the 0. And then the last one is 1/4. And again, I multiply those exponents and get that expression. So then I'm going to subtract, and I'm going to square this. So square the first, I'm going to get 1/4 e to the 2x. Multiply these two and double is the same thing I'm going to get here, but I have a subtraction sign. So I'm going to have minus 1/2 e to the 0. And then I square the last. Squaring negative 1/2 gives me positive 1/4, and then again multiply the exponent. So all of that should equal 1 once I plug in and square those expressions. So we can see some simplification is going to happen here. Let me change colors. I'm going to have 1/2 e to the 0. Now remember, e to the 0 is 1. Anything to the 0 is 1 in essence, right? So e to the 0 is 1. So I really have 1/2 and then subtract the 1/2, add the 1/2, sorry. So I get 1/2 and then plus 1/2 is 1. So I get an addition of 1 there. So I've added those together. I get 1/4 e to the 2x minus 1/4 e to the 2x. So those actually cancel out. And then I get 1/4 e to the negative 2x, and then this is a minus 1/4 e to the, that's supposed to be a negative 2x there. I had a righto. Same thing as a typo, but I wrote it. There's my righto. And then so those cancel. So I end up with just 1 that survives here equals 1, and we have proven that identity. So in any calculus textbook, when you're being asked to prove an identity, typically the process is to plug the definition of the trig function, the hyperbolic trig function, into the identity and show that we get equality. All right, so again, at the beginning of this video, we were talking about what the definitions of the hyperbolic trig functions are. We talked about kind of similarities between regular trig functions and hyperbolics. We talked about the definitions, and then we've talked about identities. Now, the real work that we're going to typically do in a section like this is the work of derivatives. So we want to talk about, what is the derivative of hyperbolic sine, what's the derivative of hyperbolic cosine, and so on and so forth. Now, I don't want to spend the time to do all of this just because it could get a little bit lengthy, but I do want to show you what we would do if we were deriving or developing the formulas. So let me scroll back to my definitions of my functions. So remember, we've defined hyperbolic cosine, hyperbolic sine in terms of exponentials. So if I wanted to derive or develop the derivative of hyperbolic sine, what I'm really going to do is differentiate all of these exponentials. So taking the derivative of hyperbolic sine is taking the derivative of these exponentials. If I do this differentiation, which I don't want to take the time to do, we actually end up with this expression. So what we find out is the derivative of hyperbolic sine is hyperbolic cosine. And we could continue that type of derivation. If we differentiate hyperbolic cosine, we're really differentiating these exponentials. If we go through that process, we actually end up with this expression. So we find out that the derivative of hyperbolic cosine actually equals hyperbolic sine. All right, so if we write these out kind of like a summary, right, if we're taking the derivative of hyperbolic sine, what we just talked about, if we actually went through that derivation, we would get hyperbolic cosine. And if we differentiate hyperbolic cosine, what we would actually get is hyperbolic sine. Now what's kind of unique here, if we think back to our original trig functions, the derivative of sine was cosine, the derivative of cosine was negative sine. So we don't have the negative based on these exponential definitions. Hyperbolic cosine's derivative is positive, hyperbolic sine. And then if we differentiate hyperbolic tangent, what we would notice is that's going to be hyperbolic secant squared. Now remember, back with the original trig functions, the derivative of regular tangent was regular secant squared. So we see the similarity here as well. And then if we did the others, let's see if I can squeeze these in right a little bit smaller. If I do the derivative of hyperbolic secant, what we find out is that's secant tangent, hyperbolics of course. And this is identical to regular trigs. Derivative of secant is secant times tangent. If we write the derivative of cosecant, and actually I have a typo there. I need to fix myself. Man, it's Monday morning and my brain isn't working here. Actually, when we differentiate hyperbolic secant, we actually get a negative. So it's slightly different than what we have for the original trig functions. There's a negative there. When we differentiate hyperbolic cosecant, we also get a negative. So the derivative of cosecant was cosecant cotangent. So we get the same thing with hyperbolics, but we have a negative here, which we actually had with trig functions. And then the derivative of hyperbolic cotangent, oops, I need my x, is going to be a negative hyperbolic cosecant squared. Okay, so we have some similarities, slight differences between the regular trig functions and the hyperbolics. So ultimately, these are the formulas, if you will, that we're going to use in a section of this nature. So at this point, we have a bunch of derivative formulas. So I have derivative formula we call the power rule. I have the quotient rule, the product rule. I have derivatives of exponentials, derivatives of logarithms, the derivatives of the regular trig function, sine, cosine, tangent, and derivatives of the hyperbolic cosines. So again, big picture here is each of the class of functions we've looked at has their own unique applications. And we're talking about how to find the rates of change of each of these functions. So what I want to do in the rest of the time in this video is let's just take a look at some examples where we would take derivatives of hyperbolics when we might have to use the chain rule, might have to use the product rule, quotient rule, so on and so forth. Okay, so let's take a look at one example here. Do a couple examples and then I'll have you try some for me. So let's say we want to take the derivative of 3 to the x times hyperbolic cosine of x. Right, now obviously this is going to be a product rule. We have 3 to the x times hyperbolic cosine. So I'm going to do derivative of the first. So I'm going to get lazy and use prime notation. Do derivative of the first times the second. And then I'm going to do first times the derivative of the second. Okay, so prior video we talked about the derivative of b to the x is b to the x ln of the base. So there's the derivative of 3 to the x. And then when I differentiate hyperbolic cosine, I'm going to differentiate cosh of x. We had just written above we get sinh of x. So there's our derivative. We're done with our derivative. You might see in a solutions manual that they factor out the common 3 to the x. So we end up getting 3 to the x times ln of 3 cosh of x plus sinh of x. All right, so again, in a section of this nature, once we've developed the ideas of the hyperbolics, we look at the derivatives and we practice differentiating functions or expressions that involve hyperbolics. Let's take a look at another example here. All right, let's say in this example we have, let's say, f of t equals ln of, say we have hyperbolic tangent. Man, I cannot write today. What's going on with me? Monday. Leave me alone, Monday. Hyperbolic tangent of t. And we want f prime of t, right? Let's find f prime of t. All right, now we can notice in this case where we have a composition. So we have the hyperbolic tangent inside of the logarithm, the log base c, the ln. So we're going to do the chain rule, right? So remember, when we do the chain rule, what we do is the derivative of the outside. So the derivative of the outside, so the derivative of ln of blah is 1 over the blah. And then we multiply by the derivative of the blah. So the derivative of hyperbolic tangent is hyperbolic secant squared. So our derivative we're going to get here is hyperbolic secant squared over hyperbolic tangent of t. All right, so personally, I'm happy with this answer. We've taken the derivative, we've used the chain rule, and we got an expression, hyperbolic secant squared over hyperbolic tangent. Now, if you're using software to check your work, you might not see this answer matching what you get out of the software, or a calculator, or even a solutions manual. So we could do some simplification here. And remember, one of the things that kind of points out to me that I could do simplification is I have secants and tangents, and I could write those things in terms of sines and cosines. So I could write, secant squared is 1 over cosine squared, and then tangent is sine over cosine, right? All of these being hyperbolics, of course. And then I'm going to flip and multiply, right? So I have 1 over hyperbolic cosine squared times hyperbolic cosine over hyperbolic sine. We can see in this case one of these hyperbolic cosines is going to cancel, right? So I'm going to end up with just one hyperbolic cosine in the denominator, and the numerator one is going to cancel out. So I'm going to have hyperbolic cosine x and hyperbolic sine x in the denominator. And then what we could do with this expression is we could write this as 1 over hyperbolic cosine of x times 1 over hyperbolic sine of x. And then 1 over hyperbolic cosine is really secant hyperbolic. And then 1 over sine is really cosecant. And this would be probably the cleanest version. This might be an answer we see come out of a piece of software or in the back of a solutions manual. All right, let's take a look at another example here where we talk about one of the applications of a weighted cable. So let's say we have, we have a tower on one side. We have some ground. We have a tower on the other side, and then we have a weighted cable between the two. And the intention of how I drew this is these towers are supposed to be equal height here. And we could talk about, let's say, with this weighted cable has the shape of a catenary. Described by, we had written this, or we had it typed for us. So we have the form y equals c plus a hyperbolic cosine. My pen does not want to follow my brain. Hyperbolic cosine of x over a. So let's suppose in this particular situation that we have the catenary y equals 20 hyperbolic cosine of x over a minus 15. Let's say here's our scenario. And let's say in this scenario, what we have is we're going to place the origin here, right? And we're going to place the x-axis here. So here's our origin. And so let's suppose that the two poles are 14 meters apart. So the two poles are 14 meters apart. Curly bracket. So what that means then is this is x equals 7 and this is x equals negative 7. So we have this function describing the shape of this catenary between these two poles that are 14 meters apart. So let's say one of the things we want to do, and I'm scooting out of my picture. Let's say one of the things we want to do is find the slope of the curve where it meets the right pole. So visually speaking, if we're finding the slope of any curve, right, we're taking the derivative. So we're thinking of the tangent. Right? What is the slope of that tangent? So we want to take the derivative of our function that models this catenary, and then we're going to plug in x equals 7 to find the slope at that particular point. So to find the slope, we're going to take the derivative of that expression. Right? So let me come back and write out what we're doing here. Let's say part A. Let's find the slope of the wire where it meets the right pole. All right. So again, that's a rate of change of our original function. So my derivative y prime, so the constant I hold off, and then I differentiate hyperbolic cosine, which we said was hyperbolic sine. Now, I want to point out to you that if I have x over 20, that's the same thing as 1/20th times x. So when I do my chain rule, right, I have the derivative of the outside, derivative of hyperbolic cosine is hyperbolic sine, and then the derivative of the inside is just 1 over 20. And then the derivative of 15 is a derivative of a constant, so that's 0, and I just won't bother writing that. So we're told to find the slope where the catenary, the weighted wire, meets the right pole. And again, that was at x equals 7. So we're going to find y prime at 7. We're going to have 20, and then hyperbolic sine of 7 over 20. So if we want to make sense of this in terms of an actual number, right, we would have to get a decimal approximation to this value. So let me bring up my calculator, and I'm going to bring up Desmos, and I'm looking at y equals, what did I have? I have y prime really, so the function that I'm evaluating, I don't even want to graph it. So we have the hyperbolic sine, and I have 7 over 20, oops, and I have 20 times that. So we can see the slope of the wire meeting the right pole is 7 point and some good decimal accuracy. Let's go to 4 decimal places. So 7.1438 to 4 decimal places. All right, now something I left off because I was, trying to rush and not have this video be too long. Let's come back to the wording of this problem that's presented to us, and let's add some actual units of measure. And so I had talked about 14 meters being the distance between the poles. Let's also point out to ourselves, or let's add the detail that the height of this from the ground, right? So if I'm looking at, let me put this in gray, right? If I'm looking for the height of the pole at any particular x value, this height is measured in meters. So let's say this is the height in meters as well. Right. So we have meters as a horizontal distance, we have meters of height. Now if I think for a moment, right, if I look at the slope of this line, the slope of the curve, what I have like rise over run, my rise over run is meters over meters. So I really have the slope being a unitless measurement there. There's the slope of my line, and meters over meters would be unitless. And the reason that I bring that up is part B, what I want to ask is, what is the angle that the wire makes with the right pole? So let's say part B is find the angle between the wire and the right pole. All right, not being really lazy with my grammar. Right? Find the angle between the wire and the right pole. Right? So I want to again kind of point out to ourselves visually, right? Here is our tower. Here is our curve. And then we had our tangent line looking like this, right? So the wire's angle between the pole is this guy. Let me do in red, right? It's this angle right here. So if we think of a triangle that we had drawn, if I think of a triangle, let's say here's the base of the triangle touching my tangent line, and then here's the height. Let me draw out here. Here's the height of my triangle. So I really have this triangle. Here's where the wire meets the pole. And so we just talked about the slope of that line is 7.1438. So if I think about rise over run, right, if I think about rise over run, I could think of this as the fraction over 1, right? So my run is 1 and my rise is 7.1438. Right? And the angle that I'm looking for is this guy right here, right? The angle between the wire and the pole. So if I think about regular trig, right, I can take the tangent of that theta, and the tangent of that theta would be opposite over adjacent. So from the geometry of my tangent line that I have here, I could say the tangent of theta, and again this is regular tangent because we're talking about ratios of sides of a triangle, so opposite over adjacent would be the tangent of the angle. And then so to find the angle, I'm going to inverse tangent both sides, right? So theta would be the inverse tangent of that number, 1 over 7.1438. So taking out my calculator, I can find out that theta is approximately, so I'm going to bring up Desmos again here, and I'm going to type in inverse tangent. So a couple different ways to do this, right? Probably the easier way is to hit the functions key, and let me go over to trig, and I can see inverse tangent here, and I'll do 1 divided by 7.1438, and we can see that that's 0.1392 if we round to 4 decimal places. All right, and keep in mind this is radians, so I need to convert. This is radians here. So I need to convert this number to degrees just to make a little more sense of it personally, right? In the US, we are used to everything being in terms of degrees. So I could leave the answer in radians, or I could convert to degrees. So I'm going to do my conversion fraction. So I want to divide off the radians. I want the degrees to survive. So in this case, what do I have? Let's say I have pi radians that's equivalent to 180 degrees. So I'm going to multiply 180 to 1392 and then divide by pi. All right, so I brought up Desmos and I did my conversion, and I see we have like 7.97 degrees. All right, so before this video gets too lengthy, one other thing you would typically see in a chapter like this in a calculus textbook would be once you discussed the hyperbolic trig functions, you would introduce the concept of the inverse hyperbolic trig functions. Now, no surprise here, right? If the hyperbolic trig functions are defined in terms of the base e exponential, right? Then the inverse hyperbolics are defined in terms of the base e logarithm, right? So base e exponential has an inverse that is the base e logarithm. So the hyperbolics definitions are base e exponentials, and therefore their inverses are log base e, right? ln. So here's the definitions. Right? I don't want to take the time to go through all of those derivations, right? You would typically see that rigorous treatment in a calculus textbook. And then now that we have these definitions, we could talk about their derivatives as well. So here's a nice little summary of all the derivatives that we talked about. In particular, down here, we can see the hyperbolic sine inverse. Remember, we can write inverses as like arc sine, arc cosine. So the arc sine, right, the inverse hyperbolic sine's derivative would be 1 over square root of 1 plus x squared, and then hyperbolic cosine inverse's derivative would be 1 over square root of x squared minus 1. Now, if you go back and you look at derivatives of trig functions and derivatives of inverse trig functions, again, these are all really similar to the derivatives of inverse trig functions. Okay? So we could spend 20 to 30 more minutes doing more examples where we take derivatives of inverse hyperbolics, where we do the product rule or the quotient rule or the chain rule, so on and so forth. I feel like probably at this point you're pretty comfortable with product rule, quotient rule, chain rule. So showing these formulas, I will assume that you're relatively proficient in doing those other types of problems, or you would be looking in your textbook to get some more practice of that nature. So this ends the video on hyperbolic tangents, or excuse me, hyperbolic trig functions. And this ends the video on the overall chapter of derivatives of all different types of functions. All right, I look forward to speaking to you in the next chapter, where we're going to delve deeper into derivatives and their applications in context or real-world problems.